Before we start, we have our next quiz will be on Friday. Today we will complete chapter 5, discussing compounds with more than one stereocenter, as well as discussing the physical properties of stereoisomers. And so the quiz on Friday could be on anything from chapter 5. Then many of you have discovered that the exams have been returned. The exams are in the return boxes in the hallway, and the answer key is posted. And so these stats are combining both classes, not just this class, but the 1 o'clock class as well. So we had a high of 98, an average of 81. The average on the first exam is usually the highest of the averages in this class. The tests do tend to get more challenging as we go. And the average historically on the first exam is usually somewhere in the low 80s. So we fell in that historical range, which I think is a good achievement. This is not a normal semester. We had many students going in and out of quarantine over the first 3 or 4 weeks of the semester. And so I think that's a pretty good accomplishment that we could get a result that was pretty normal in this abnormal semester. So we like to recognize students who do well on the exam. We have the cookie awards here that we'll hand out. So Preston, who's filming, got a cookie award last year, and he told me he was so excited that he took a picture of it and he kept it as the screen of his phone for weeks afterwards. So these are highly coveted awards. Noah Moran, will you please come on down? He has a cold. Well, that's a shame. I was hoping he'd be celebrating his high score. But Minnie Cho, then, please come on down for us. And let's give Minnie a round of applause. So Minnie is a chemistry education major, so she wants to teach high school chemistry after she graduates. She's from Monterey, California, which is a beautiful city, very fun place to visit with lots of interesting history. And she enjoys singing and playing the guitar. So hopefully we'll get a nice music video, extra credit music video submission from you, Minnie. Okay, congratulations. And then close on Minnie's heels, Morgan Hart. Morgan, come on down. Yes. All right. Morgan Hart is from Draper. She wants to go to grad school after she graduates. And we both share the hobby of mountain biking. Mountain biking is one of my favorite things to do. So what's your favorite biking trail? The Corner Canyon trails. That's what I figured. Since you're from Draper, the Corner Canyon trails are nice. I usually like to go to Midway. Wasatch Mountain State Park has a lot of nice trails that are not as crowded. But anyway, a lot of great mountain biking trails in the area. So you should all check them out if you're looking for ways to exercise that are good for social distancing. Mountain biking is one of those that's very good. All right. So for the next exam, what we will do is we'll recognize our top scorers, but we will also recognize students who improve the most from exam 1 to exam 2. So if you didn't do as well as you wanted on exam 1, then you need to look at the answer key, try to figure out why you missed the questions that you did. Feel free to come and talk to me. My office hours have been fairly underutilized to this point in the semester, so there's plenty of opportunity for you to come into my office, one at a time, of course, during office hours, and discuss the exam. The TAs are also available for help on the exam during their recitations, as well as their scheduled office hours on Zoom. So make sure you figure out why you missed the questions that you did, and then develop a plan for improving on the second exam. And with good fortune and hard work, then you could be recognized with a cookie award on exam number 2. One other thing I'll mention about the exam is that the TAs do an excellent job of helping me to grade the exam, but we are humans and occasionally we make mistakes. And so you should look closely at the key and at your questions, your answers, and if you believe you have earned more points than you were awarded, then you can make a case in writing, right? Write a few sentences explaining why your answer matches what's on the key and why it deserved more points. And you can turn that into me along with your test anytime within the next week up until next Wednesday. And then I will look at those all together and do any regrade requests all at the same time in order to do it in a consistent fashion. And of course, I'll look at the ones that you have mentioned to me, but in the interest of fairness to students who don't turn in regrades, I do look at the whole exam because sometimes scores that were given in your favor are canceled out by ones that, or scores that you were not given as many points as you had earned or balanced out by errors that were made in your favor. But if you have any questions at all about how the test was graded or not understanding the correct answers, please feel free to come by my office and talk to me. I think that the test should be, in addition to a way of assessing your knowledge, it should be a learning tool as well. And the only way to learn it use it as a learning tool is to find out why you missed the questions that you did. Okay? All right, so let's talk more about stereochemistry. So we talked mostly on Monday about compounds that have a single stereocenter, and we learned how to assign that stereocenter as R or S. At the end of class, we had an iClicker question where we had a molecule with 2 stereocenters. So today we're going to talk more about compounds that have 2 or more stereocenters. And there's a formula here. 2 to the n is the maximum possible number of stereoisomers when n is the number of stereocenters. So if we have a compound with 2 stereocenters, how many possible stereoisomers could we have? We could have 4, right? 2 squared is 4. That doesn't mean there are always 4 stereoisomers. Sometimes there's 4, sometimes there's 3. It simply depends on the presence of the presence or absence of planes of symmetry, as we will see in a moment. So that's why this says maximum number of stereoisomers, because we don't always observe that maximum number in nature for a given compound. Taxol or paclitaxel, I showed you, the anti-cancer compound from the bark of the Pacific yew tree that I showed you on Monday, that has 11 stereocenters. So you see that there's a huge possible number of stereoisomers of that compound, and only one of those exists in nature. So it's pretty amazing that the enzymes in that tree form Taxol in only one of the possible 2 to the 11th stereoisomers that could exist. Okay? So let's look at some compounds with 2 stereocenters and draw them and see if we can figure out how many stereoisomers we have and how those are related. And the way we're going to draw them is in an eclipsed conformation where the backbone of these 4 carbons is eclipsing as opposed to our usual staggered conformation. And I'll explain why we're doing that in a moment. But first we'll just draw our sample molecule is going to be called 2,3-dibromopentane. Okay? When we have halogen substituents coming off of a chain, we name them as halo, meaning we drop the "ide" or the "ene and we add O, so we call this a bromo substituent. So this is 2,3-dibromopentane. Okay? And we'll just call this compound A for now. And then we're going to make our mirror. We're going to draw the backbone as the mirror image of the one I drew on the left. And then we're going to mirror our substituents. Okay. So we have A and B. These are mirror images of each other. Are they superimposable? Okay, I see heads shaking. They're not superimposable. Okay, if you superimpose this backbone on that one, you have to flip it. You find that the bromines aren't going to match up, so that they're not going to be superimposable. So non-superimposable mirror images, what do we call these? Okay, so these are enantiomers of each other. All right? So that's 2 of the 4 possible stereoisomers of this compound, 2,3-dibromopentane. So now what we're going to do is we're going to change the configuration at one of our 2 stereocenters and keep the other one the same. Okay. So we've drawn a compound that doesn't match A or B. We'll call that C. And then we'll make its mirror image in the same way we made the mirror image of A. Okay. And this one we'll call D. So are C and D superimposable? Okay. No, they're not. C and D are not superimposable. And so how are C and D related to each other? Okay. So A and B are enantiomers. C and D are enantiomers. So many times what happens when we have a compound with 2 stereocenters is we end up with 2 pairs of enantiomers. So that's what we have here. A and B are enantiomers, C and D are enantiomers. But how are A and C related? Are A and C stereoisomers of each other? They are stereoisomers. They have the atoms connected together in the same way, but a different orientation in space. Are A and C enantiomers of each other? No, they're not even mirror images, so they can't be enantiomers. So we need a new vocabulary word to describe the relationship between A and C. And that word is diastereomers. So diastereomers are simply stereoisomers that are not enantiomers. Okay? So if we have compounds that are stereoisomers, either they're enantiomers, meaning they're non-superimposable mirror images, or they're not. And if they're not enantiomers, they're going to be diastereomers of each other. So we can say A and C are diastereomers. We could say B and C are diastereomers. We could say A and D are diastereomers. B and D are diastereomers. Okay? Any questions about diastereomers versus enantiomers? Okay, let's examine a related compound, but we're going to take off one of the carbons from our chain. We're going to look at 2,3-dibromobutane, and we're going to do a similar analysis looking at its stereoisomers. Okay. Okay. So we'll call this one A, 2,3-dibromobutane. Again, we're drawing the backbone in an eclipsed conformation as opposed to the staggered conformation we usually see. And I will explain in just a couple of minutes why we're doing that. We'll make the mirror image. Okay. All right, A and B, are they superimposable or not? Okay, they don't superimpose. Right, in this case, you can just take this and plunk it right on top, and you find that the bromines don't match up. So indeed, A and B are not superimposable. Okay. So let's change one of our two stereocenters here. We'll call that C and make our mirror. You don't always have to draw these mirrors in, but I'll do it here on the board. Okay. C and D, are these mirror images of each other? Are they superimposable? Okay. So they cannot be enantiomers if they're superimposable. They are the same compound. Okay. So C and D are the same. So when 2,3-dibromobutane only has 3 stereoisomers. It has A and B, those are our enantiomers, and then C, which is identical to the one I drew here in D. So is C chiral? Is this a chiral molecule? No, it is not. Our definition of chiral is non-superimposable on its mirror image. Since C is superimposable on its mirror image, it is achiral. Does C contain stereocenters? Are there carbons in C with 4 different groups attached? Yes, there are. And I warned you on Monday that when we have 2 or more stereocenters, sometimes those molecules are not chiral, and this is an example. So we need a new definition, a mesocompound. That's my abbreviation for compound that I like to use. So a mesocompound is an achiral compound that contains stereocenters. Okay. So C is a mesocompound, whereas A and B are chiral, but they all contain stereocenters. Okay. So what's the relationship between A and B? They're enantiomers. What's the relationship between A and C? Diastereomers. So what we learned from this is that an achiral compound can have diastereomers, right? C is not chiral, but it has diastereomers. A and B are diastereomers of C, okay? And there's a figure in your book that summarizes the relationships between these compounds right here. So if you look closely at the structure of C and compare it to A and B, there's something that C has that A and B do not. What is that? Yes. A plane of symmetry, yes. So C has a plane of symmetry. Okay. So this is why it's very helpful when you're trying to determine if a compound is chiral or not. It's very helpful to draw it in this eclipsing conformation. Because if the backbone is eclipsing, then it's easy to see if there's a plane of symmetry. We just cut the backbone in half to where one half reflects on the other, and we look and see if the substituents reflect on each other or not. So we see that that happens with C, and it does not happen with A and B. Okay? Fortunately for us, if a plane of symmetry applies to just one conformation of a molecule, it applies to the molecule as a whole. So even though this eclipsed conformation is going to be a high energy conformation for that molecule, if there is a plane of symmetry, it applies to the molecule as a whole. Okay, so if you're looking for planes of symmetry in acyclic compounds, you want to draw them in this eclipsed conformation because it's easier to see if those planes of symmetry are present or not. If you're given a structure that's not drawn in that eclipsed conformation, then you want to rotate it so that it is, and then you can see if the plane of symmetry is present or not. So there's another principle related to compounds with two or more stereocenters and enantiomers versus diastereomers, and that has to do with the R and S nomenclature. So we can assign R and S for the individual stereocenters in these molecules. So let's do that for A. And we're going to put a number in front of each R or S. So this is carbon 2 right here. Is carbon 2 R or S? We know the bromine will be group 1. We know the hydrogen will be group 4. Okay, it's S, right? This is group 2 over here, and that's group 3. So 1, 2, 3, counterclockwise is S. Okay? Carbon 3, R or S? So we got 1, bromine is 1, hydrogen is 4. Which one is 2? This or that? The one with the bromine is 2. So we go 1, 2, 3, and we find that it's 3R. Okay? What we find is that the enantiomer of compound A is going to be exactly opposite in terms of its R and S assignments. So if we look at B, this is carbon 2 in B. We go 1, 2, 3. So we see that carbon 2 is R. And then at carbon 3, 1, 2, 3, we see that it's S. Okay? So this is a way to check your work. If you're not sure if compounds are enantiomers or diastereomers, you can determine the R and S assignments for each stereocenter. If they are enantiomers, those R and S assignments will be opposite each other. If they are diastereomers, some will be the same and some will be different. If we only have 2 stereocenters, to be diastereomers, you would have to have one center be the same and the other one be different. So let's look at A and C, and we don't even have to figure it out. We can just look at carbon 2 and we see that carbon 2 is opposite. So we can just say that C is 2R, and then we look at carbon 3 and we see that it's the same. And so we just see that that is going to be 2R, 3R. And then, of course, since D is the enantiomer of C, we know that that's going to be 2S, 3S. We could check that by looking at B and seeing that it's the same as B at carbon 3, but different from B at carbon 2. Okay? So this is a good way of checking your work. Diastereomers are going to be different at one, same at the other. Enantiomers are going to be opposite in terms of the R and S configurations. Any questions? Okay, so let's look at disubstituted cycloalkanes. So when we looked at our acyclic alkanes, we drew the backbone in this eclipsing conformation in order to see if we had a plane of symmetry or not, to be able to identify a potential meso compound. So with cycloalkanes, we're just going to consider the planar conformation. We know the planar conformation is very high in energy due to torsional strain. We know that there's going to be a very small fraction of a percentage of that available at equilibrium. But as we learned, if a plane of symmetry applies to just one conformation of a molecule, it applies to the molecule as a whole. So we're just going to consider the planar structures, planar conformations of our cycloalkanes in determining whether or not they are chiral. Okay? So we're going to look at 1,3-dibromocyclopentane. Is this cis or trans? Okay, this is our cis isomer. Cis 1,3-dibromocyclopentane. Okay. Okay. Is cis 1,3-dibromocyclopentane chiral or achiral? Achiral, exactly. Okay. It is a meso compound. It has a plane of symmetry. And if we consider the planar conformation, we would have the plane of symmetry just cut right through carbon 2 and right through the bond that's connecting carbon 4 to carbon 5. Okay. Now we're going to draw trans 1,3-dibromocyclopentane. Okay. Chiral or achiral? Chiral, not superimposable on its mirror image. And so here, the trans isomer is chiral. So we could call this A and B. These are going to be enantiomers of each other. And what's the relationship between the trans isomer and the cis isomer? They're diastereomers of each other. So A and B are enantiomers, and they are chiral. And then A and B are diastereomers of the cis isomer, which is a meso compound and achiral. Okay? Any questions about those definitions and those relationships? Okay, then you should be ready to practice. Let's get our eye clickers out. We have two molecules drawn here on the screen, two structures. Please talk to your neighbors and determine the relationships between these structures. Okay? All right, we'll give you maybe 15 or 20 more seconds to come up with your final answers. Okay, any more? Going once, going twice. Okay, how are these compounds related to each other? They are the same. Yes. Who would like to describe how they figured out that they're the same? Yeah, go ahead, Grace.
So I noticed that there were two up and one down
Okay.
of CL, and that the two fit together. So I thought trans, and then I thought cis of one of them. But then I realized it's the same for the other molecule, like kind of like trans, kind of like
Okay.
cis.
Right?
But yeah, if you just flip it upside down, then
Uh-huh. Yeah, it's hard to use the terms trans and cis when you have three substituents as opposed to two. You can say that these two are cis and these two are trans. So what you noticed is that the pattern, the up-down patterns of the chlorines were the same in the two molecules. It's that you had up, up, down, and then over here you had down, down, up. But if you just rotate that 180 degrees, it would be up, up, down, right? So you saw that same pattern, and that told you that those compounds were the same, okay? Or at least it would tell you that they are mirror images of each other. So how would you know that they're superimposable? You could rotate them and you could superimpose them, but is there a shortcut way to figure out they're going to be superimposable? Is there a plane of symmetry? Okay, there's a plane of symmetry. It's easiest to see in this one because it just cuts right through this bond here that's pointing out at us. Just right there. In this one, the plane of symmetry kind of goes diagonally, right in between those two chlorines that are mirroring each other. So we see that there's a plane of symmetry. So that tells us that this is a meso compound. Tells us that those mirror images are going to be identical. Okay. Any questions? Yes, Morgan. The mirror images would be non-superimposable, and there would be no plane of symmetry. Okay, so that would have to be the case. With a three-membered ring, I don't know if you can have it not have a plane of symmetry. Any way that I can think in my head to arrange those groups, you're going to end up with a plane of symmetry somehow. That's not the same with all rings, of course. But so three-membered rings, for some reason, are the hardest to see. Um, just I don't know what it is about our brains that makes us harder to see the relationships there with three-membered rings versus five or six, the ones that we're more used to seeing. So if you understood this problem, then you are in pretty good shape and you have a pretty good understanding of this concept of chiral versus achiral with cycloalkanes. So we have a couple of figures from the book. Here we have this chart, an organizational chart for isomers. These are all the types of isomers we're going to learn about in the class. So now we have them all. They're either constitutional isomers or stereoisomers. And then stereoisomers are divided into enantiomers and diastereomers. And then we have a flow chart for a decision-making process to decide what type of isomer two different compounds would be. The book likes to focus on issues of nomenclature for determining if compounds are constitutional isomers versus stereoisomers. I prefer to use that as a way to check my work, and I prefer to look at are the atoms connected together in the same way or not. I think that's a better way to determine if compounds are constitutional isomers or stereoisomers. But going through a process like this will help you decide the relationship between two compounds. Okay, question, Morgan. So meso, so those would be, if you were comparing two mirror images of a meso compound, you conclude that they're the same compound, right? So you wouldn't even hit this point. But if you were comparing a meso compound to its chiral diastereomer, then you'd end up down here because you determine that they are stereoisomers, but you would determine that they're not mirror images of each other. Okay? Other questions? Okay, let's talk about physical properties of stereoisomers, starting with the physical properties of enantiomers. Okay? So the physical properties of enantiomers are going to be almost identical. Enantiomers will have the same melting points, the same boiling points, the same solubility in water or organic solvents. But they differ in two areas. One is the way in which they rotate plane polarized light. That may seem like an odd property, a fairly esoteric property. Maybe it is, but it does have some significance we'll talk about in a moment. And then the second way they differ is the way in which they interact with other chiral molecules. We showed you that with our demonstration on Monday. Our hands are chiral, and our mirror image hands interact differently with a single type of baseball mitt. So in the same fashion, enantiomeric molecules will interact differently with a single enantiomer of another chiral molecule. Okay? So let's talk about the plane polarized light issue. Here we have a schematic of an instrument known as a polarimeter. A polarimeter has a light source which produces unpolarized light that's oscillating in all possible planes. Then we pass that light through a polarizing filter. So now we only have a single plane of light, known as plane polarized light. That plane polarized light passes through a sample tube, which has a solution of an optically active. We'll define that term for you in a moment on the board. What it means is that you either have a single enantiomer of a chiral molecule, or you have a mixture of enantiomers that is not one-to-one, that has an excess of one enantiomer over another. Okay? What happens is as the plane polarized light passes through that optically active sample, let's just say it's optically pure for now, a single enantiomer. That single enantiomer is going to rotate plane polarized light, and then we have a detector that's going to detect that angle of rotation. And that is known as the optical rotation of that substance. And there's a formula in the book, which we're not going to go into, that shows you how to calculate the optical rotation. So a pair of enantiomers is going to rotate plane polarized light with equal magnitude, but in an opposite direction, either clockwise, which is known as plus, or counterclockwise, which is known as minus. Question?
Is it too complicated to explain here why it rotates?
Yes. The short answer is that there's no symmetry at that carbon, and so that lack of symmetry, when that light hits a chiral molecule because of the lack of symmetry, it's going to rotate. But I can't explain it in any more depth than that. But I can show it to you. We have a very crude polarimeter here. You can make a polarimeter from an overhead projector, a pair of polarizing filters. Okay, so what we have here is light, plane polarized light, and we can put our second polarizing filter on top, right? And we can rotate it various ways. We can rotate it so that it shuts off the light. There's no light coming through our crude polarimeter. We could take a substance that is achiral, such as water. Okay, water is achiral. So if we put water in our polarimeter, it is not going to rotate the plane polarized light, and we won't see any light coming through our polarimeter. Okay? So there's our water, nothing happened. Okay? Here we have a beaker with corn syrup. Okay, corn syrup is a carbohydrate material. Carbohydrates are chiral. They're produced in nature as a single enantiomer. So this is an optically active, actually an optically pure sample of a carbohydrate. So if I put this in our polarimeter, the plane polarized light is going to be rotated as it passes through here, and now you're going to be able to see it pass through that second polarizing filter because it has rotated. So let's watch that. Take out our water, put in our corn syrup, and now we can see light is passing through in the area where it has gone through the corn syrup because it's been rotated. Okay? So chiral molecules do indeed rotate plane polarized light. Any questions? Okay. So let's learn a little bit of vocabulary, and then we're going to talk about some other physical property relationships. Okay? So on the screen here, you saw the term optically active. Let's define optically pure first, okay? A substance that is optically pure is going to be a single enantiomer. Okay? A substance that is optically active is going to be a mixture of enantiomers that is not 1-to-1. Okay? So if you have a 5-to-1 or 10-to-1 mixture, then that is going to be something that you would call optically active. And technically, optically pure is actually a subset of optically active as well. Okay? Yes, question.
If you have something that's not a liquid, but it's like a solid or something, then would this principle still have an effect?
Yes, you would dissolve it in a solution, usually of an achiral solvent, so that that solvent would not interfere. But if you dissolve a chiral solid in an achiral solvent, you can still see this effect. Okay? And then we have another term, racemic mixture. So a racemic mixture is a 1-to-1 mixture of enantiomers. Okay? A racemic mixture will not rotate plane polarized light because as the plane polarized light travels through the sample tube, it will hit an essentially equal number of the two enantiomers, and it will rotate clockwise when it hits one enantiomer, and then rotate back counterclockwise by the same magnitude when it hits the other enantiomer. So the rotations will cancel each other out. So racemic mixtures will not rotate plane polarized light. Achiral molecules will not rotate plane polarized light, but optically pure and optically active samples will. Question?
Is there a differentiation between racemic mixtures and achiral mixtures?
Yes,
Okay.
absolutely. So water is achiral, but if you have a 1-to-1 mixture of A and B, that's racemic. That's chiral, but racemic. Okay, so there's definitely a distinction. The end result of the rotation is the same, but there's a distinction between those types of compounds. Okay, and then there is one equation. We're not going to teach you the specific rotation equation because that's really not very useful unless you're doing research, and at that point you can learn that. Percent enantiomeric excess, or percent EE. That refers to if you have an optically active mixture, the percentage of the major enantiomer minus the percentage of the minor enantiomer. So if I have a 90-10 mixture of enantiomers, what would my percent enantiomeric excess be? It would be 80. Right? If I had an 80-20 mixture, what would my percent enantiomeric excess be? It would be 60, exactly. So that's how we calculate percent enantiomeric excess. Okay? Any questions about optical rotations and the various terms? Yes?
What does EE stand for again?
Enantiomeric excess. The excess of the major enantiomer over the minor enantiomer. Here we have a table summarizing the physical properties of enantiomers. One thing that this table points out that we haven't mentioned yet is that the melting point of a racemic mixture is often different from the melting point of the individual enantiomers. The individual enantiomers will have the same melting points, but a racemic mixture can have different melting points. The reason for this is that a racemic mixture of a chiral molecule will pack together differently in a crystal than a single enantiomer will pack together in a crystal. And so it will take different amounts of heat or energy to turn that solid into a liquid. So even though enantiomers have the same melting points and boiling points, racemic mixtures do not have to have the same melting points or boiling points as those individual enantiomers. Okay? But their solubilities will be the same, and then we see the relationships in optical rotations. So let's talk about diastereomers now. Diastereomers have different properties. They're not like enantiomers, which have the same properties except for a couple. Diastereomers can have different melting points, different boiling points, different solubilities. They might not differ by much, but there's no law that says they're going to be the same like there is with enantiomers. So let's take a look at this table. This shows some fairly famous compounds. These are stereoisomers of a compound called tartaric acid. So tartaric acid has 2 carboxylic acid groups, 2 alcohols, very water-soluble substance. You can see the solubility here. So what we see here with tartaric acid, it has 2 stereocenters. And one of its isomers has a plane of symmetry, so it's a meso compound. So C is a meso compound, and A and B are enantiomers. And as we see in the table, the physical properties of C, we'll get to this in a moment, the physical properties of C differ from the physical properties of A as well as B. C is achiral, so it has no optical rotation. This symbol here is the symbol for optical rotation. And then we also see that our racemic mixture of tartaric acid has a different melting point than the individual enantiomers do. And the water solubility of the meso compound is different. In this case, it's less than the individual enantiomers. Okay? Don't worry about this DL thing. That's ancient nomenclature that we're not going to go over. I will only look at the RS. So tartaric acid occurs in grapes. The plus enantiomer, compound A, is the naturally occurring one. There's tiny amounts of its enantiomer that are going to be present in grapes, but predominantly you're going to get A, and then C doesn't exist in nature. Okay? You can make it in a lab, but it doesn't exist in nature. So in the mid-1800s, Louis Pasteur, who I'm sure you've all heard of, he lived in France. He was French. Winemaking was big in France, and tartaric acid is produced in the winemaking process. And sometimes it crystallizes. And somebody, I don't know who thought to do this, but somebody found out that usually when you put the crystals from tartaric acid in a polarimeter, it would rotate plane polarized light. And we would expect that because I told you that A is the one that exists mostly in nature. But sometimes they would get some crystals from their winemaking process. They'd put in a polarimeter, and it wouldn't rotate the plane polarized light at all. Maybe they were drinking too much of their wine, and that's what made them decide to put these crystals in the polarimeters. I don't know what the thought process was, but we're glad they did it because it helped them discover some fundamental principles of organic chemistry. So Louis Pasteur was curious about this. Why did the crystals sometimes rotate plane polarized light? Why did they not do it in other cases? So he took a microscope, and it turns out that these are giant crystals. They're really, really big, and he could look at them under the microscope well enough to see that the ones that didn't rotate plane polarized light were comprised of 2 mirror image forms. He saw that these crystals were mirror images of each other. And he took some tweezers, and he separated those mirror images. And he put them individually in the polarimeter, dissolved them in a solution and put them in the polarimeter, and found that they did rotate plane polarized light in opposite directions. Okay? So Louis Pasteur was the person who discovered, and he put this in the literature, that there are mirror image molecules, right? That you can have mirror image molecules. And this was revolutionary because tetrahedral carbon was not discovered until 25 years later. So nobody had any idea of the 3-dimensional shapes of organic molecules in the mid-1800s. And so Louis Pasteur didn't know how these mirror image molecules could exist because tetrahedral carbon had not been discovered yet, but he knew that that's what was causing these mirror image crystals, these mirror image molecules. Okay, so that's the significance of chiral, of optical rotations, and the significance of tartaric acid. All right, one last thing. We've already talked about how the interaction of enantiomers with other chiral molecules is different. This is actually the only way we can separate enantiomers, because usually we separate compounds according to differences in their physical properties. So if enantiomers have the same physical properties, we can't separate them. So we would have to use another chiral molecule that interacts differently with each enantiomer to separate it. That's why that drug thalidomide was given as a mixture, a racemic mixture of the two enantiomers back in the 1950s and 60s. So another example of how chirality affects the body is with the sense of smell. We have olfactory receptors in our nose, shown in cartoon form here. Those olfactory receptors are proteins. Those proteins are made up of amino acids, which are chiral. And so we have a single enantiomer of each of these olfactory receptors in our nose. So they're going to interact differently with enantiomers. They're going to bind differently according to hydrogen bonding, van der Waals forces, and so forth. In a normal year where we don't have pandemics, I would pass around samples of two enantiomers and let you smell them, and smell that and verify that they indeed have different smells. But this year, I'm just going to have to draw them on the board, and you'll have to take my word for it. This is a molecule called carvone. Okay, I've drawn here on the left the S isomer. The S isomer happens to smell like caraway seeds. Okay. Hopefully I've drawn this correctly as the mirror image. Okay, so this here is the R enantiomer. The R enantiomer of carvone smells like spearmint. Okay, so if we could pass those around, you'd each get the chance to verify that indeed enantiomers interact differently with those proteins in our noses, but unfortunately you'll have to take my word for it for now. Any questions? Yes?
So it's a cool example with our nose, but like, how would you use something like that to separate things?
So if you had, there's a couple different ways you can do it. You can use chromatography, where you pass a solution of the enantiomers through a column, and the one enantiomer will interact with the chiral substance on the column more strongly than the other, so it will elute from the column in different order. That's one way to do it. Another way, known as resolution, we'll learn about in 352, where you actually do a reaction to make diastereomers, which can be separated, and then you cleave off whatever that extra group was to give back the enantiomers. So that's one we'll understand more in 352. But for now, the chromatography one is one that we can understand. All right, we'll see you on Friday. Make sure to pick up your exam and be ready for our quiz that we'll have.